Hello everyone, welcome to the 8th lecture of the lecture series on open channel flows. In this lecture, we will continue our discussion on uniform flow in open channels. Now in the last lecture, we started discussing on uniform flow in open channels. We discussed the basic aspects of uniform flow, and also we had an extensive discussion on two very popular resistance formula or resistance equation in context of uniform flow. Those are given by Chase's equation and Manning's equation. Manning's equation, as we mentioned, that is the most widely and extensively used equation in context of open channel flow. Is very popular for all the field engineers and for all the solving all the practical open channel flow problems. So with that background, let's have some more further insight of the Manning's equation. So we also mentioned that one of the Manning's roughness coefficient given by n is one very important parameter in context of Manning's equation. And so let's discuss on the factors which really affect the Manning's roughness coefficient. The Manning's roughness coefficient is a representation of the integrated effect of the channel's resistance. So it's a representative of the channel roughness, and it's affected by factors like surface roughness of the channel, the vegetation cover in the channel, and let's say the irregularity in channel cross section and the alignment of the channel. Of course, among these factors, the channel roughness is the most vital one, and influences the value of the Manning's roughness coefficient the most. In the last lecture, we also discussed some empirical equations which to estimate the value of Manning's roughness coefficient. These empirical equations, they relate the surface roughness to the surface roughness, or some representative value of the surface roughness to the Manning's n. And like the Strickler's equation, remember in Strickler's equation, Manning's n was proportional to the surface roughness raised to the power 1/6. So in the empirical equation, n is proportional to some representative value of the surface roughness, let's say D50 or D90, which is raised to the power 1/6. Meaning of the statement is, if the roughness varies, there's a huge variation in the surface roughness in the value of epsilon s, there is hardly any major change in the value of the roughness coefficient n, as n is proportional to the surface roughness raised to the power 1/6. Dependence on of n on the vegetation cover is dependent by the type of the vegetation. It may be grass, it may be small weeds. It also depends on the height of the vegetation and the cover and its density. All these factors have some influence on the value of n, and also sometimes determining the actual value influence of these factors on the value of n. It's complicated. It depends on, again, the experience of the person who is handling it. And at low velocity and small depths, the value of n becomes higher than at high velocity and higher depths. So this is also one important characteristic of the value of n, as when there is a grass cover or a weed cover on the channel bed. Regarding the third point, the irregularities in channel cross section and alignment of the channel, all this add up to the resistance of the channel. And of course, when there is much irregularity and in cross section and alignment of the channel, it yields a higher resistance of the channel, and of course for that case the value of Manning's N will increase. Now in some channels the Manning's roughness coefficient might not be same throughout the weighted perimeter. So in some channels different parts of the weighted perimeter may consist of different surface roughness elements, and so having different might have different value of Manning's N. So for such channels it is necessary to determine an equivalent or composite value of the roughness coefficient, so that it can represent the whole weighted perimeter of the channel cross section, and so that we can apply Manning's formula for the whole for the flow in the channel. So there are techniques to estimate this equivalent or composite roughness coefficient, and it's essentially calculating the weighted average of all the various roughness present on the channel bed. So in doing so, what we can consider is that the whole weighted perimeter of the channel is divided into a number of sections P1, P2, P3, Pn, and those the value of the Manning's roughness coefficient corresponding to those weighted perimeters are N1 into N3 Nn, and the weighted cross sections for those perimeters are A1, A2, A3 Nn, such that the sum of all the cross sections of the subsections equals to the whole cross section of the flow, given by the last equation on this slide. So on the on your right on this slide, you can see a schematic representation of what we are discussing now. So this channel cross section or the weighted perimeter, you can see that it is divided into n number of subsections, and those subsections are based on different roughness, surface roughness, given by Manning's roughness N. So here, in calculating the equivalent or composite roughness, we assume one thing, that the mean velocity of flow through each of the subsections given by V1, V2, V3 are all equal to the mean velocity of flow of the whole cross section given by capital V. So in other words, V1 is equal to V2 is equal to V3 is equal to capital V. Manning's equation can be invoked here, and in doing so we can apply Manning's equation for the for each and every section of the whole cross section of flow, and we can write that S naught to the power half is equal to V1 N1 by R1 to the power 2/3 is equal to V2 N2 by R2 to the power 2/3, and so on, which again equals to V, capital V into N by capital R to the power 2/3. So this is of course the Manning's equation. We're writing in its form, in some other form, and here R1, R2, R3 and capital R R1, R2, R3 are the hydraulic radii of the subsections, and capital R is the hydraulic radius of the whole cross section. And hydraulic radius, as we know, is a ratio of the weighted cross section by weighted perimeter. So what we can write from the equation above is that AI by A whole to the power 2/3 equals to Ni Pi to the power 2/3 by N into P to the power 2/3. So for the ith section, we can write this formula, this equation that is given by what we just have mentioned. And manipulating this equation, we can write the last equation of this slide, which is highlighted in blue and is given by N equals to sum of Ni to the power 3/2 into Pi whole raised to the power 2/3 and divided by P to the power 2/3. So N here is of course the equivalent or the composite roughness coefficient of the whole channel, and thus we can use this value of the coefficient in the Manning's equation for the whole cross section as a representative value. Moving on further with the discussion of Manning's equation. So Manning's equation can be written in the discharge form as Q equals to 1 by N A into R to the power 2/2/3 into S0 to the power half, or it can be written as Q equals to K into S0 to the power half. Here K is a coefficient given by 1 by N into capital A into capital R to the power 2/3, and K is one parameter which is known as the conveyance of the channel. And looking at the equation, we can say that the coefficient K denotes the discharge capacity of a channel per unit bottom slope of it. So if S0 is 1, K equals to Q, and so it actually represents the discharge capacity of a channel essentially. If we take the Manning's roughness coefficient on the other side, we can write Nk equals to A to the into R to the power 2/3, and this term A into R to the power 2/3 is called a section factor. So like the conveyance of the channel, we can say that A into R to the power 2/3, this product is also a kind of representation of the discharge capacity of a channel. Now let's try to calculate the section factor given by A R to the power 2/3 for a trapezoidal channel. A typical trapezoidal channel has been shown in the diagram on your right. So the bottom width of the trapezoidal section is capital B, the flow depth is small y, and the side slopes are given is m is to 1. And so for this channel, the weighted cross section is given by capital A equals to under bracket B plus my into y, and the weighted perimeter is given by capital P, which equals to B plus 2y under root m square plus 1. So we can calculate the hydraulic radius, of course, by dividing the weighted cross section by the weighted perimeter, which is given by R as shown on this slide. And if we calculate multiply it with we calculate A R to the power 2/3, it becomes a function of the bottom width of the channel capital B, the side slope m, and the flow depth y. the function is shown by the equation a r to the power 2/3 equals to under bracket b plus my to the power 5/3 into y to the power 5/3 divided by under bracket b plus 2y m square plus 1 raised to the power 2/3. So this is the function. Now note that for a given channel means the bottom width and the side slopes are given or pre-designed or designed. So in that case, the section factor a r to the power 2/3 becomes only a function of the flow depth, or a r to the power 2/3 is a function of y. Now if we plot the equation, the function what we have derived in the last slide, it becomes something, whatever what is shown by the diagram, in the diagram on this slide. Here note one thing, that the section factor has been non-dimensionalized, and the function is called phi, and the flow depth is also non-dimensionalized by the bottom width of the channel. So on your or on the ordinate you can see y by b, while on the abscissa you can see the function phi given by a r to the power 2/3 by b to the power 8/3. So here the variation of the flow depth with phi has been shown for three values of the side slope. M equals to 0, m equals to 1, and m equals to 1.5. M equals to 0 essentially imply the channel cross section is rectangular, while any value of m greater than 0 implies that the section is trapezoidal. And note one very important thing here, that for all the curves that is presented, the flow depth becomes a single valued function of the ratio phi. So in other words, the flow depth is a unique function of the section factor here. So this type of channels for which m is greater than equals to 0 or is known as the channels of the first kind. And for the channels of first kind, remember the flow depth is a unique function of the section factor. Now section factor is, again, as we have already mentioned, the section factor is a representation of the discharge capacity of a channel, and using Manning's equation we can write a r to the power 2/3 equals to qn by s naught to the power half. So for a given channel, the n and s naught, they are fixed. So for the channels of first kind, there is only one value of flow depth possible for one discharge value. So this is another very important aspect of the channels of first kind, that for a uniform flow through a channel of first kind, there is only one value of flow depth possible for one value of discharge, and this flow depth is known as the normal depth. So the normal depth can be defined as the depth of flow at which a fixed discharge passes through an open channel of the first kind as uniform flow. Now Majority of the channels, let it be natural or let it be man-made, they are of the first kind. So for which the top width increases with height. So that is the channel of first kind. However, in some cases we also encounter channels which are just the opposite of it, for which the top width is closing, or the closing top. For example, channels like circular channels, ovoid channels, or triangular channels with the vertex upward. These are the channel shapes with closing top, and for these channels normally this m is less than 0. So m has a negative value. So this type of channels are known as the channels of second kind. Now if we plot the same function same function phi, which we against the flow depth, which we did for the channels of the first kind, we arrive at some plots or curves, which is shown by the diagram on your right. Look at these diagrams are really non-linear, and one important aspect of this diagram, looking at it, we can say that at some regions, at some parts of the curves, the flow depth becomes flow depth is not a unique function of the section factor anymore. So in other words, for one value of the section factor, or as section factor is a representation of the flow discharge. So for one value of discharge, at it's in the channels of second kind, maybe two flow depths are possible as normal depths. I'll repeat that once more, that for the channels of second kind, for a particular value of discharge can have, for a particular value of discharge, more than one value, two values of flow depth is possible, which can flow as uniform flow. So this is rather one very important result for the channels of second kind. So that's all for this lecture. We will continue our discussion on uniform flow in the next lecture, where we'll try to calculate the normal depth, and also we will discuss one very important thing, that is the hydraulically most efficient cross sections for uniform flow. So thank you very much.